let's continue to the next speaker. It's our pleasure to have Lucas Menon. He's a senior lecturer at Imperial College London, Department of Mathematics and Imperial X. He was a PhD student at ETH Zurich and a postdoctoral researcher at the University of St. Gallen and an assistant professor at University of Munich. His research is in the intersection of mathematics, machine learning, and finance. So please, Lucas.
Okay, so thanks a lot for the kind introduction. Thanks a lot for inviting me to this very interesting conference. So my talk is also trying to address the various audiences. So yeah, sorry about that. Yeah, so my apologies if some things are redundant for some people, but yeah. So let's start. So also in the fields of deep learning, so applying deep learning to PDEs and stochastic processes. So there it has been shown that neural networks work well in many applications. So one example that I want to mention is deep hedging. So this is a deep learning algorithm that is now also really used in financial industry. And so I think this is so the fact that such a deep learning algorithm is used in financial industry means that it's really important to understand well firstly why this method work, but also so how reliable are they, and so if you train them right, do you have convergence? Are there do you have possibilities to give guarantees for convergence? And so this is what this talk is about. And so I started at the end of my PhD with really applying deep learning to financial problems, but then I got more interested in actually some understanding this theoretically. And so let's start with something that you all know. So this is a universal approximation result, a classical theory formulation by Hornig. Right, so this is something that probably everyone in this room has seen in some form, right? So the statement is can be formulated as follows. So you fix the bounded continuous and non-constant activation function. Then you look at the set of one hidden layer neural networks here. And so where you vary the parameters A, B, and W. And then this set is dense in the set of continuous function on so a given compact interval X. Right. And sorry. Yeah, so this is of course very important for the foundations, but of course it doesn't tell you anything about the actual neural network, right? So it just tells you there exists one, but you don't know how large the network needs to be. So how many terms n you need here in this sum for to achieve a prescribed accuracy epsilon. So so this was in the 90s, right? So there's been enormous progress on understanding this better. In particular, so all that we know about our unknown function that we're trying to approximate is that it has certain smoothness properties, right? So that the function itself is k times differentiable, and also that its derivatives are continuous and satisfy certain bounds. Then the number of nodes that we need, so the number of terms that we need in the sum that we've seen on the previous slide, is of order epsilon to the minus d over k. So if we want to achieve accuracy epsilon, right? So epsilon is very small, epsilon to the -1 is very large. And so in particular, if k is fixed and d becomes very large, right? This grows exponentially in d. That's often referred to as the curse of dimensionality. Now, deep neural networks, so this was for shallow neural networks, deep neural networks are provably more efficient, but still for such smoothness classes of functions, they don't overcome the curse of dimensionality. So you still have this exponential dependency. So in specific situations that have been shown to be able to overcome the curse of dimensionality, so including compositional functions, Barron functions, which can also be thought of as functions where the smoothness somehow varies, it depends on the dimension. And finally, also for solutions to certain partial differential equations. So this is what we're interested in here. Right, so there is a brief overview on certain classes of so-called Kolmogorov PDEs. So these are PDEs associated to stochastic processes. And so there has been a lot of interest in these PDEs and trying to understand conditions under which deep neural networks can overcome this curse of dimensionality for approximating such PDEs. Right? So solutions to such PDEs. So you have, so here's a list of recent results. And so, for instance, if you want an application example from finance, so if the data that you're observing in the market is described well by such a model, then what these results say is that in principle, they can be approximated well by deep neural networks. So these results, in that sense, so they provide approximation rates. So given an accuracy, they tell you what network size you would need. And here in more detail, so one of our recent results, so you consider an unknown function that lies within a certain class of PDEs. So all you know about the function is that it's a solution to such a PDE. You don't know the actual functions sigma, mu, and this kernel mu here. So this is a this is a generalization of the diffusion equation with an additional term here corresponding to a jump process, right? And so you don't know the coefficients, the actual coefficients, but you know that the unknown function that you're trying to learn satisfies such a PDE for some coefficients in a certain class, right? And then one can prove that you can then approximate this solution to the PDE by deep neural networks without the curse of dimensionality. So the approximation error is of size c times d to the p times m to the minus alpha. So where these constants c, alpha, and p, they don't depend on the dimension or the number of parameters, right? And so you see that this is essentially, so this tells you how quickly does the error converge to zero if you make the number of parameters large, right? So it converges to zero at rate alpha. And the constant in this error bound only depends on the dimension polynomially. So in particular, if the dimension is large, you don't have an exponential growth in the dimension. Let's look in a bit more detail at the constant coefficient case. So this is the PDE corresponding to an exponential Levy model. So if this kernel nu here is zero, then you're only left with the part above. And then this is the so-called Black-Scholes equation. But so here it's more generally where you also have a jump term. And then, so I want to give here precise conditions, right? So what I'm saying is, so we need, because we're interested in the dependence on the dimension d, right? So of the inputs, we look at this PDE solution for each dimension d. And now what we assume on the class of those PDEs, so what we assume on the unknown functions is that we have some upper bounds independent on the dimension on the coefficients in here, right? So the diffusion coefficients and the drift coefficients in the PDEs, they don't blow up as the dimension grows. And similarly for the moments of this jump measure nu. Then just to fix notation, so we're looking at deep neural networks, and what we call the size of a deep neural network is just the number of non-zero parameters, right? So you look at the network and you count how many non-zero parameters do you have in that network. And then, so we proved following result. So, right, so let the functions ud be as above, and so assume that the initial condition of the PDE, so in the finance context, this would be the payoff of the option that you're trying to calculate the price of. So suppose this can be approximated, so this is this phi d here. Suppose this can be approximated well by a neural network, right? So meaning that there exists a neural network whose size only grows polynomially in epsilon to the -1 and d, which, so sorry, a family of neural networks, the Lipschitz coefficient, so these networks are all Lipschitz. And yeah, so you have that they approximate well. So, right, if you make epsilon small here, this goes to 0. So, yeah.
So phi d is the function that satisfies this PE that you had earlier?
No, phi d is the initial condition. So, right, so this is the initial condition. And so in at least in mathematical finance context, this phi d is often given as a maximum of you know, the components of your inputs minus something, and then minimum, and so composition of such functions. And so in that case, it's really, so this phi d is actually given exactly by a ReLU network. And in that case, so I mean, that's somehow where this assumption comes from. In that case, you can really make this assumption satisfied. So this is always 0, and so it's satisfied naturally.
But I guess what I'm missing is
Yeah.
that what is the connection with the PD? Right now, you're just saying they exist in the network. But
Yeah, so this is now the assumption on the initial condition. So UD is the solution. Now here, this is the assumption on the initial condition. Now we say, okay, under these conditions, you find networks, right? So you find a family of networks that approximate the solution to the PDE at the final point to accuracy epsilon, and these networks only grow polynomially in the dimension.
Okay.
So basically, this means that deep neural networks can approximate the solution to these PDEs without recursive dimensionality. Yeah, just that you see what kind of results we have been interested in. Yes?
Is there anything specific or
so now we looked at the fixed time point, but so you would like to have it also for several time points. I mean, yeah, so this is a good question. So, right, so if you have a discrete number of time points, yeah, you could easily build a network which kind of does it all. But if you have a continuum, yeah, we didn't think about it a lot, but it's an interesting question. I agree. Yeah.
And if
Yeah.
it's just an existence result, or can you actually say specifically what neural network satisfies it?
No, it's an existence result, and that's what will motivate the rest of the talk.
Okay.
But so just that you get a flavor of what's happening. So basically, in the end, what you'll do to prove this is you use a so-called Feynman-Katz representation, which allows you to write the solution of the PDE as an expectation. And then basically what you do is you use, so this can be used to bound the first term here. Then to bound the second term here, it's basically a truncation, because so what you do is you truncate your Levy process. And the third term is somehow the key step where where you actually construct the network to some extent. So what you want to do is you want to construct a network to bound this difference here. So this is something deterministic, but the way that how you prove it is actually a stochastic argument. So what you do is you say, okay, let's look at basically a Monte Carlo average of this expectation here, and then prove such a bound here, which you can do by using Rademacher complexities. So a combination of Rademacher and Gaussian, because this is multivariate here. So once you have a bound of this type, because the bound holds an expectation, you also get that the bound holds for a realization of this random sum here. And so this allows you to construct, to at least show existence of a network. Yeah, just a flavor. If you're interested in more details, I'm happy to give you more, of course. Then just that you see what kind of directions are of further interest. So this was now for this constant coefficient case. So we were also interested in the general jump diffusion case, right? So where you have general coefficients here, and also here. So this is now a jump diffusion process, right? So if you drop the last term, it's just a diffusion process. With this one, it's a jump diffusion process. And what you need in order to do a similar argument is actually, so you need to approximate this solution to this PDE by some approximation process which will again allow you to construct a neural network. And that approximation process, what you need to do. So firstly, you need to discretize time. So that's why you have this little h here, right? So firstly, you discretize time, then you approximate the coefficients by neural networks, right? So this gives you the epsilons here. So discretizing time gives you this grid here. Then you truncate the small jumps here. So right here you have jumps over all of RD. So what you need to do here is you say, okay, let's just look at the jumps which are bigger than a certain threshold. And finally, you have this integral here. So for the large jumps, you can decompose this in sum and an integral. And for the last term, you do a Monte Carlo sum. So in principle, this is an idea that you can explain on one slide, but actually, doing the error analysis and getting a bound like that is unfortunately quite a bit of work. It's feasible. And so once you have a bound like that, you can proceed similarly as on the previous slide. So again, it's just an existence result. Now a third result that I recently obtained is concerned again in exponential Levy case with the so-called optimal stopping problem. So where you want to find so you look at such an expectation and you maximize over all stopping times. So in finance context, this is relevant for so-called American options, but there are also many other applications of optimal stopping problems. And so you see here, you have a similar type of condition and you can get a similar conclusion. So really just a flavor of what can be done. So what's in all these results, right? So these results somehow show existence of neural networks and address the question of expressivity, right? So they show, okay, also really in high dimensions, you can find neural networks that approximate these solutions to PDEs or optimal stopping problems well. But of course, you have the question, okay, how do you learn now these parameters? And so far, among existing results for such learning solutions to PDEs, there are really no results that address the full learning error, right? So the existing results address approximation. Some of them also generalization. So in the sense of proving something for the empirical risk minimizer, but no results actually prove a bound on the difference between the solution to the PDE and the function learned by stochastic gradient descent to approximate that solution, right? So just to make it explicit here, right? So sometimes some results prove that the empirical risk minimizer can be approximated well, but what you then do in practice is, right, even approximate that further by stochastic gradient descent. So the challenge is really to handle all three errors simultaneously. So approximation, generalization, and optimization. And so what I want to show here is the first setting in which you can really do that by changing a little bit the training algorithm and by looking at a little bit smaller class of PDEs. So the PDEs that we look at are again of exponential Levy type with an additional non-degeneracy condition. And for training algorithm, we look at single hidden layer networks where we randomly generate the hidden weights and only train the output layer weights. So in that case, of course, analyzing the optimization and also the generalization error is relatively simple. The key question is then, okay, what about the approximation part? So essentially the results that I presented in the first parts, they're not applicable anymore, because in these results, you need to be able to tune all the parameters, right? Still, so in this setting, you can actually really analyze all three learning terms, and you get a neural network-based algorithm that is fully implementable and where you can prove that it doesn't suffer from the first dimensionality. So this is still not what you'd actually do, right? Because in principle, you would probably still use deep learning. but it gives you a benchmark. And also if the weights don't move much, right? So it gives you kind of still, yeah, some first results to start with, get the full convergence. Yeah.
There is a difference between this approach and the kernel regression. You are fixing the random race, which can be random feature, and then the other part is linear.
Well, I mean, I'm sure you could get similar results for kernel regression, but I will get to that. So the key difficulty is really the approximation error again. So as in the previous ones, in the previous results, the key point is kind of the expressivity part, because analyzing the learning part is not difficult here, right? Yeah. Yeah.
Just a question about the, I guess the proof is like you're saying they can learn, or they're able to learn, and you're somehow looking at the set of functions that can be learned by HTTP. So like you look at the specific updates and like
I'll show you. I mean, the rest of the talk will be devoted to this results.
Okay.
Yeah. So as I said, so the key part is actually getting in an approximation bound. And so, right, so basically, right, we decompose the learning error as approximation, optimization, generalization. And as I said, so the key difficulty is the approximation part. And so the class of functions that we're interested in are such shallow neural networks. So we're now, right, so compare this to the slide with Hornick's theorem. Right, so now we consider these weights WI here as trainable, whereas the AI and BI are randomly generated from a previously specified, so a density that we specify. And then, so yeah, so what can you prove? So we look at the function h, which has such a Fourier representation here. So this is the function that we're aiming to approximate. So right, h has this Fourier representation here. So think of G as the Fourier transform of h. And now you suppose that this G satisfies this integrability here and some further integrability, which, so in this further integrability condition, you have this f bar up here, and you have this pi w up here. So the pi w was the density from which you draw the random weights AI here. So this was the density of this one. And the f bar, so think of pi w as a density with polynomial tails, then f bar will be polynomial. So this you can easily check. And so basically what this is here is just the polynomial of the norm of psi. Now, depending on the tails of pi w, you have a stronger or weaker integrability condition here. But essentially, this is just a further kind of polynomial integrability condition on the Fourier transform of h. And if that is satisfied, then you can show that there exists a w such that you have this, so the expectation of the error here, of the uniform error here, between the function that you want to learn, h, and this random neural network here, you have has satisfied this bound where n, so n is the size of the network, right? So in particular, this bound goes to 0 at rate 1/2. Yeah.
Is this constructed similar to random features?
Yeah, I mean, so this is somehow, but it's, so the I would say the addition is that we are starting from a function which has this Fourier representation, and we show that you can actually carry out the whole thing, right? So it's really the approximation error part that is kind of, but yeah, I mean this what we're doing here is random network features, right? Yeah, but so if you want, we show that such functions are in the kernel Hilbert space associated to these features, right? That's what we show. So typically people assume, okay, let's assume we have a function in that space, right? And we show now, okay, so this function here is really in that space somehow. And the reason why we need that is because now we want to use it to such solution to such PDEs and show that such solutions to such PDEs actually satisfy these conditions. That's so we're again back with the PDE considered previously. Again, special case Black-Scholes PDE. And now we make, because we want to also analyze the dependence on the dimension of the constants again, we make some explicit assumption on the distribution for which these features are sampled. And so we choose them to be heavy-tailed. So we generate them from multivariate t-distribution and a univariate t-distribution. Right? And so what we ultimately consider is this ReLU network here with t-distributed weights here and here. Okay, and so only this vector W is trainable. And now, so how much time do I actually have?
8 minutes.
Okay, okay. And then, so we formulate the learning problem, right? So we assume we have IID data points, and so the solution to the PDE is the regression function in that problem. And so the key example is, of course, that you observe noisy observations of the solution to the PDE, right? So you have some data which you collected, and now these are noisy observations of the PDE. And you want to learn based on this data, you want to learn the solution to the PDE. And yeah, another application is also some PDE solvers, which are based on empirical risk minimization. So this was introduced here. But so this is just another example of a setting which fits in here. But the most important one is really observing such noisy observations of the solution to the PDE. Then we could do either regression, constrained regression, or in order to be able to compare it with other methods. So we looked at stochastic gradient descent here, but it's really just standard stochastic gradient descent, where with the additional, where you project back to a ball of size lambda in case the parameter goes out of this ball. But otherwise, it's really just standard stochastic gradient descent. And then what we're interested in is the learning error, right? So to come back to your question, so we're interested in looking at the test error, right? So here you have the solution to the PDE evaluated at an independently sampled test point, and you look at the difference between the solution to the PDE and the random neural network also evaluated at that point and with trained parameters, right? So these are the learned weights after t steps of stochastic gradient descent. So as I said, instead, you could also use regression or constrained regression because of this random feature setup. And yeah, so the result that I'm showing on the next slide, so there are two other additional results, but which I'm not showing here. But so they're very similar. And in these cases, yeah, so you would train by regression or constrained regression. And so then you can prove the following result. So you assume that you have the following non-degeneracy condition. So you assume that in the PDE that you're looking at, the diffusion term is somehow big enough, right? So this is a condition on non-degeneracy of the diffusion matrix. And you also need some integrability on the initial condition or the payoff, and some more technical conditions on the moments or bound, so on where your data actually lies on which you're evaluating the PDE. And then you can show that when you train the random neural network by stochastic gradient descent for t steps with lambda of order 1 over square root of n, then you get the following bound on the test error, right? So where you have, you have a constant that doesn't depend on the dimension, doesn't depend on the number of network parameters, it doesn't depend on the number of data points, and it doesn't depend on the number of gradient steps, right? So this is a constant here. Here you have a dimension of the PDE to some polynomial power. So again, not exponential. So you don't have cursive dimensionality. And then you have three terms. So the first one, right, is 1 over square root of n. So this goes to 0 as you let the number of the size of your network go to infinity. This goes to 0 as you let the number of samples go to infinity. And so once you have fixed n, right? So this also goes to 0 as you let the number of gradient descent steps go to 0, to infinity. Yeah.
So when you define the vector f, you need to take the expectation of the first pair.
No. No, so this is,
Single realization of the
yeah, so this is randomly sampled weights.
just one.
I mean, you have, because you have n weights, right? You have kind of n times d or n times d plus 1 random variables that you sample. Yeah, no, but the idea is that you really randomly sample and somehow get from this kind of nice or sufficiently rich, yeah, sufficiently rich set of features. And now that, so that's what you use for then training.
Expectation is taken over all the randoms.
So here then the expectation is taken over all the randomness, right? Yeah. But because things are independent, I mean, if you want some conditional on something, you can also get something conditional, right? Or high probability, or yeah, but it's really over all the randomness. Yeah. So yeah, for instance, coming back to your question, right? So you could say, okay, with high probability, these random weights give you a bound that satisfies this condition, right? Does that answer the question? Yeah. Okay.
You have another question there?
Ah, yeah.
Also have to wrap up.
Okay. Yeah. Yeah. I mean, I'm really done. Yeah. So.
So if I understand correctly, you have your input X, you have your observation, also observation Y, you have like the curve. So you essentially start by the error between the two solution and your predicted the one predicted by your model. You minimize this error, right? But so like, a similar approach has been done by physical information neural networks where they do this. And on the parallel side, so they also add another, let's say, regularization to the loss, which enforces the PD. But here there seems to be no enforcement of the PD. It seems like you mention some points, you generalize, but you are not enforcing.
Oh, but so physics informed neural networks are used to solve the PDEs. So these are used when you know the coefficients of your PDEs, right? So you know. No, but so you know the solution of your PDE usually, and what you're trying to do is because you need to know the coefficients of the PDE in order to, because otherwise you can't write down the loss function.
No, it's,
Yeah, but so you need to know the coefficients, right? And
you essentially calculate. You can calculate. They say this is calculation. I don't know the parameters. But here.
okay, yeah, sure. No, you can do that. Yeah. Yeah.
It seems like power down of a pin.
Well, I mean, if you can prove that it works, then I'm happy also with the pin, right? But no one has proved it, right? So no. So that's the point I'm trying to make here. So if you want a simple setting in which, so if you can prove it for pin, then yeah, that's a really great result. Yeah. No, but I agree. I mean, so this is something that's definitely very interesting as well. Yeah. So yeah, just a little wrap up. So you can, so you have these assumptions here on these on the phi's, but so when you do an experiment, so when you do experiments, you see that it seems that these are not necessary. So you get still the same rate of decays when you use a function that doesn't, so at least for the functions we've tried, so where you don't have these precise conditions, but you still get somehow decay that matches what you expect from the theoretical results. And that's all I want to say, actually.
Maybe you have a couple minutes for questions, additional questions.
One. Like I know you did this construction by Baron. I think he's also using like Fourier transforms and stuff.
Yes.
Is there anything in your analysis that is somehow similar?
Yeah, absolutely. I mean, so I mean, similar in the sense that, so maybe I have here, because this could be interesting. So because what happens in Baron's proof is that so he takes this function that he wants to approximate, And he writes down a integral representation based on the
Yeah.
Fourier transform.
That you're gonna have cosine and sine. function,
Exactly.
And then to approximate and he's using this what we call band functions.
Yeah, exactly.
So that's something-
And so this proof here, you do something similar. But so the first thing you do is you write down, so this h is the function that you want to approximate,
Yeah.
and you show that based on the conditions, you can get such an integral representation, but now not with a sine and cosine, but with a ReLU. And this is somehow based on I mean, it's not the same, but it was inspired by a paper by Baron and Krusovsky, I think 2018, where they do something similar like that, but yeah, it's still, so it's inspired from these ideas. And then the second part is inspired by the classical Fourier features result by by the proofs of these but somehow combining all this. The other thing that you also need, so to get the bounds on generalization and optimization, you need to have also bound on the W, so on the readout. And this is somehow then also connected to the unknown function here. So this is a further, because right, so you need a bound on this for the whole for the other parts, for the approximation, for the generalization optimization errors, and this also comes from this construction.
Okay.
Yeah.
Short question. This might be slightly orthogonal, but there is a field of trying to learn the actual equations, but not the solution.
Yeah. So you mean like learning the coefficients
Yeah.
somehow? Yeah, no, I mean, that's also, of course, very interesting. Yeah. But I haven't looked at it. I mean, yeah, so the goal was really, because there's no case where everything has been proved. So the goal was really to find at least,
Yeah.
one interesting case where you can do everything and then see from there what you can do.
One last question. Can you use this for sampling? So let's say I have like a PD which comes from some like stochastic differential equation associated with some mixed measure, etc.
Yeah.
And then let's say I have an algorithm which can give me a couple of samples, but it's very expensive. So can I use this approach to like develop like an insane algorithm?
Could be. I mean, I haven't thought about it, but it's an interesting idea. Yeah. Yeah. Thanks.
Let's think, Lucas again.
Thanks a lot for.
So now we have 10 minutes, right?
Yeah, 10 minutes, correct, yeah.
10 minutes.